Okay, thank you for listening to my AMS Tropical 2021 talk. This is Matt Onderlinde from the National Hurricane Center. The title of the talk is an Ensemble-Based Statistical Hurricane Intensity Prediction Scheme, Computing Ships from the ECMWF Ensemble Prediction System. The objectives and goals of this study. The objectives are to compute ships forecasts using the ECMWF EPS members, and that's quite a task in and of its own. But then to identify ways in which these statistical forecasts can aid NHC's forecast process and messaging in regard to uncertainty, for example. So the goals are to quantify uncertainty using the ensemble data, provide useful intensity forecast guidance to the hurricane specialists if possible, and then identify scenarios where the dynamical and statistical forecasts diverge, and then see if we can use that information to improve the statistical schemes. So some quick background on ships. DeMarie and Kaplan in 1994 introduced the ships model. It's been refined a lot over the years, and it's updated annually with new coefficients and training data. It's been leaned upon heavily for tropical cyclone intensity forecasting over the years. A little less so recently with the improvements in the dynamical models, but it's still used quite a bit today. It uses environmental predictors and model forecast fields to approximate changes in TC intensity. You can see some of those predictors listed there, and if you want more information on ships, you can see this URL at the bottom. Then some background on the ECMWF ensemble prediction system. It's a 50-member ensemble with a control run as well. The grid spacing is 18 kilometers in the horizontal, and it has 91 vertical levels. At the Hurricane Center, we have global gridded fields available for the 50 members in Grid 1 format out to 10 days. So some sample output before we get into more details. We have an example on the left here of a track plot from the EPS ships output. And you can kind of see there how the spread's actually fairly tight. This is for Hurricane Delta in 2020. But you can see the intensity increasing there to Category 2, 3 in the Gulf of Mexico. And on the right, you can start to get an idea of forecast intensity variability in the ensemble. The box and whiskers, of course, show that intensity expanding as you go out further in the forecast time. Now, some of this is due to landfall timing uncertainty, of course, but still you can start to see how there could be some useful information here with regard to intensity uncertainty. Another useful thing is just to compare the ship's output to the dynamic output from the ensemble. And so on the left, we have the same plot as before, where we're showing intensity forecast from the ship's output, which is statistically modified. And then on the right, we have the dynamic output from the model itself. And what you see right away is that the ship's process increases the intensity forecast substantially there. Where we had very few hurricane forecasts from the dynamic ensemble, we have almost explicitly hurricane forecasts from the ship's ensemble. So more details on the methodology. One key difference is that what we're doing here is running the GFDL vortex tracker on each EPS member. So ships, what it does is it follows the OFCL forecast track and then computes its predictors along that official forecast track. But what I'm doing in the EPS system is running the tracker and then letting that track guide ships. So ships is being calculated along each individual member's track. And I think that will help improve the variability in the intensity forecast that comes out from the ensemble. We're still borrowing the GFS-derived coefficients for now. A future project may be to recompute those using EPS data. We generate ships, D-ships, and LGEM forecasts. Those are all variates that come out of the statistical models of ships. But everything that I show in the results from this talk will reflect the D-ship variety of the output. So then I'll compute an ensemble mean for each case. And also I wanted to try computing an ensemble mean along the OFCL forecast. So for those, I take the 25 members with track forecasts that are closest to OFCL and compute the ensemble mean from those cases, those members. Now there's two ways we can do this. We can run in what I call no lag mode or real-time mode. And no lag mode it's kind of like the ideal world scenario with unlimited computing, where we can generate forecasts very quickly and have them available immediately. And then the other version is real time, and that's more like what we have in operations today at NHC, where we'll be running ships using the current conditions as defined by NHC, but then with 12-hour-old EPS model data. And I'll show results in both forms. So the other thing about this project is that it's very data intensive. The data sets are very large, and due to that, I couldn't really rerun an entire season at this point, mostly due to networking constraints and data volume. But so what I wanted to do was identify a regime in which the intensity forecasting was more challenging, and then focus on that regime and see if the EPS ships could provide some value in that area. So I ended up with approximately 210 cases that were from the Atlantic and East Pac seasons, based on the intensity forecast and how it relates to TC initial intensity. And so these nice graphics on the right, provided by Ben Travang from CIRA, what they show is that the intensity initially in this 35 to 50 knot range tends to correspond to the largest forecast errors in the, at least for 72-hour forecasts and 96-hour forecasts. So in terms of our 3-4 day forecast range, it seems to be storms that are initially in this 35 to 50 knot range that are the most challenging. So those are the ones that I focused on. I also prioritized them by the TC's peak lifetime intensity. So the stronger a TC ever became, then those were more likely to be selected in the cases that went into this study. Okay, so now going into some of the results. So first I'll show the no lag scenario. So remember, this is the cases where it's an ideal world where we have unlimited computing and we can crank this stuff out in 10 minutes and provide it right away. So what we see is that, surprisingly, at least in my opinion, this technique performs quite well competitive to other guidance from NHC. You'll notice that if we look at 60 hours, it's actually the most accurate intensity model compared to HICA, HWRF, and GFS, and D-ships, and some of the others that are used today at NHC. So that's interesting. This is the Atlantic, and again, this is kind of the ideal scenario, so it's not something that would be possible right now in real time. So quickly looking at this result in the East Pac, it's a little less flattering there. It doesn't do quite as well, although until the end of the forecast where it's actually the best model. But again, this is kind of our ideal world scenario. So now we'll look at the results in the real-time scenario. So this is using the 12-hour-old model fields. And surprisingly, again, these EPS ships forecasts are pretty competitive with models that NHC is using. I forgot to mention on the previous slide, the ensemble mean is the thick red line, and the ensemble mean following the official forecast, the 25 members closest to official, is in the thick purple line. So you can see it's kind of middle of the pack here in the Atlantic again. Slightly low case counts, and hopefully we'll run this in real time this coming season, and we'll get a lot more cases. We can make a fair comparison. But it's certainly an interesting result. It seems to show that there may be some promise in using this as an actual forecast aid. These specific results for real time are kind of similar. Again, not so great in the middle of the forecast, and then more competitive towards the end. So I kind of mentioned this briefly, showing the track plot comparisons, but what this figure shows is it's the mean absolute error for the ensemble mean dynamical system in orange and the ship system in blue. So all this is really showing is that you get a nice correction in the intensity forecast error by applying the ship's technique to the ensemble. So we can be confident that we're improving its intensity forecast in this process. So now we'll go into quantifying uncertainty. So how much does this EPS ships technique give us in terms of quantifying that uncertainty in the forecast? And I'll have to say that these results were a little bit disappointing. I was hoping we would see stronger correlations here. But so what we're looking at is OFCL forecast error in knots on the y-axis, and the standard deviation of the 50-member ensemble EPS ships on the x-axis. And so as you can see, there's a lot of spread. The R-square value is very small. So now this doesn't take into account any of the land effects like landfalls or anything like that. So it's certainly possible. There's other ways to look at this. I did also try the spread, the max forecast minus the min forecast from the ensemble. It produced very similar results. So the initial look seems to suggest there may not be a lot of information in terms of quantifying the uncertainty, but we'll have to see. So these next few figures, I'm just going to go forward in the forecast time. So this is 36 hours. Here's 48. It gets a little better, but then we go to 72 and it gets worse again. So just not convinced, going back and forth a couple times here, just not convinced that there's a whole lot of uncertainty quantification available with at least this standard deviation method. And this is definitely an area I plan to spend some time investigating to see what other ways I can do uncertainty quantification using this ensemble system. So a quick summary: the EPS ship shows some promise in terms of being used as an intensity forecast aid. Seems to have limited ability quantifying uncertainty, so a little bit disappointing, but this is an area I plan to put a lot more effort. We'll see what we can pull out of it. And it provides the system provides a nice improvement upon the ability of the dynamic system to forecast intensity. So we know that at least for an 18-kilometer ensemble like this, we can still gain a lot by processing it statistically. Quickly, some future plans. I do plan to run this experimentally in 2021 and hopefully for all model cycles. So after a full year, I'll be able to do a full apples to apples comparison on a whole season, which I think will be a nice result, and it'll give the forecasters something to go on in terms of the future. We'll look at other ways to quantify uncertainty, removing land. If you have any ideas, reach out to me. I'd love to hear your ideas on how to improve this uncertainty quantification. And then down the road, rederive the coefficients using the EPS data itself, and then generate a GEFS version of this whole scheme as well. When I originally started the project, we were still on the previous version of the GEFS system, but the new system shows a lot of promise, and I think it would be worthwhile to do this with that as well. So thanks for listening.